Okay, so welcome to the first official quick seminar of the fall semester. We've been running this virtually over the summer, and we're going to continue to do that over the fall. So for those of you who are new, here's the format that we generally follow. So our speaker is going to give the talk virtually, and then if you have questions during the talk, you can enter them into the chat, and then I'll read them out loud. And also, after the talk is over, we have some time reserved for extended Q&A and for further discussions. So for the talk today, we are pleased to have Professor Mark Wilde as our speaker. Mark is a faculty member at Louisiana State University, and he has done extensive work on quantum communication, quantum cryptography, computational complexity, and other fields. Today is going to be talking about quantum Renyi entropies, and these have been a central topic for a long time. I remember when I first started working in quantum information, they were a hot topic, and they've continued to be a central tool since then. So I will turn it over to Mark.
Okay, thanks, Carl, for the introduction, for having me. It's nice to be able to speak to y'all. I know I'm due to visit y'all for a seminar in person. So maybe, I don't know, maybe in a year that'll be possible, and it would be nice to do that. Yeah, so this I'm going to give you an overview on quantum Renyi relative entropies. There have been a lot of developments over the past decade. I made a lot of slides. I'm not going to be able to get all through them all, but I'll make them available so you could look through them. I'm just going to give you a sense of three major notions of quantum Renyi relative entropies and their applications in hypothesis testing, entanglement-assisted communication, and the third topic is feedback-assisted capacities, but that's the one where we probably won't have time to get to it. Okay, so this title that I made, I don't know, for me it was kind of a joke. So I noticed, there's a trend where people will just say something and its use, and they'll make that the title. And I just thought that was kind of funny because it doesn't really tell you that much about what you're using the thing for. So I think this was started by Dennis Petz, and it's relevant to be citing him here also, and to be following his legacy, because he was the one who first developed quantum Renyi relative entropies. And he has a famous book. It's just called Quantum Entropy and Its Use, and it can be worthwhile to go through that. And then he continued this, and then, I'm friends with Felix in real life and on Twitter, and we kind of joke a lot. And, his PhD thesis was called Relative Entropies and Their Use, but he did say like where they're useful for, so that was interesting. And then also Maxim Shirokov. And then, after thinking more, I tried to figure out, okay, what can I do to this title to make it even more academic sounding? And so often in academics, you see "on the" as like a prefix for a title. So then that's how this title came about. Okay, so what is our motivation? These concepts of entropy and relative entropy, they're really at the core of information theory and physics. And then when you look to find generalizations of these notions, Renyi generalizations are quite relevant, and they do have operational meaning like entropy does. And the interesting thing that happens, so if you're coming from classical information theory, there's really only one way that you define entropy and Renyi relative entropy. But then when you go to the quantum case, there's potentially an infinite number of ways to generalize them. And what's interesting is that some of these different ways find use and have precise meaning. Okay, so what I said is I'll talk about three of them and their applications. Okay, so entropy, this is one of the most famous formulas in all of science. I don't know if you saw the movie Arrival, but when I was watching this scene, this was one of the first things that caught my eye, that the entropy formula was there on the whiteboard. If you haven't seen the movie, not to give too much away, but the one thing that happens is they try to communicate with aliens. And I guess, obviously, if you're going to be communicating with aliens, you will need the entropy formula. So I guess that's how it came up there on the board. Okay. What was its main meaning? This is what Shannon gave to us many years ago now. It's the optimal limit of classical data compression. Okay, so then going from entropy, you can have a generalization of that called relative entropy or Kolbach-Leibler divergence. This is the formula for it. Many of you have probably seen it before. P is a probability distribution, and Q does not have to be a probability distribution. It can just be a non-negative measure, and that's useful for recovering other entropies from the relative entropy formula. And it's an interesting looking formula, but it has a operational meaning in hypothesis testing. And so when we go to the quantum case, we'll talk about that, and then the classical meaning of relative entropy will emerge also. And its main purpose is it's a distinguishability measure from which you can make information measures. Okay, so some special cases. Entropy itself is a special case of relative entropy. If you plug in the vector of all ones into the formula in the previous slide, right here, and you put a minus sign in front, you recover the formula for entropy. So entropy is a special case. Also, mutual information is a special case. So if I have a joint probability distribution and I plug in the first slot, and then I plug in the second slot, the product of the marginals, you get mutual information. Okay, and so.
Can I ask a question, Mark? Can I ask a question?
Yeah.
So are you allowed to plug in a vector of all ones because it's like not a aren't you supposed to plug in like only distributions like that are?
It's okay.
Okay.
You can plug in a vector of positive numbers, and that's fine. And it's useful to allow for that. It might lose this meaning in the hypothesis testing, but up to some like rescaling, you can bring it back to a probability distribution and retain the meaning. Okay, and then another kind of formula that's useful, it's not obvious, in this talk, I'm not going to be giving detailed proofs. I'm just going to be like stating facts. And then these kinds of things, you can find them in books. But you can recover the formula for mutual information by allowing an optimization over probability distributions over Q. You could allow for an optimization here as well and still recover the mutual information formula. But somehow when generalizing mutual information to Renyi mutual information, this kind of formula has found quite a bit of use. Okay, so what is one of the most important properties of relative entropy is its data processing inequality. So let's review that for the classical case. We'll call it classical channel N. That's, to be consistent with the notation we'll use for the quantum case that's coming up. So if you send in a probability distribution or a measure through a channel, you'll get an output. And how do you compute the output? You just do this kind of sum over the input letters. Okay, and then this is the data processing inequality. And it's really important. Many things follow from it. Many things related to resource theories and second law of thermodynamics kind of statements. Here we just interpret it as distinguishability does not increase under the action of a classical channel. Okay. So now Renyi relative entropy, this is work that came along about roughly a decade after Shannon's work and Kolbach and Leibler. This is the formula that Renyi came up with. And there were, after Shannon came up with this work, there were a number of axioms for entropy. And I believe the branching property of entropy and relative entropy, if you drop that, then you get the Renyi entropy and the Renyi relative entropy. So that's what Renyi was thinking about. And it's nice, this nice formula. You now have a whole spectrum of relative entropies that depend on an alpha parameter. Okay, so again, you have special cases of it. So if you plug in for Q the vector of all ones, you put a minus sign in front, you get the famous formula for Renyi entropy. And then Imre Cezar, famous classical information theorist at the same Renyi Institute in Hungary as Petz, he proposed this formula for Renyi mutual information and gave interpretations of it. And so that's where the second formula that I gave for mutual information comes into play for generalizing mutual information. Okay. So that's the, and then there are certain properties of Renyi relative entropy which make it interesting and useful. First of which is it's connected to the relative entropy. You obtain it in the limit as the parameter alpha goes to 1. And to show that, you need to take derivatives and use L'Hopital's rule. Okay, the other thing is that it does have a data processing inequality. So for all values of the alpha parameter, you have this data processing inequality. It's additive. I didn't say that about the entropy and the relative entropy, but those ones have this property also. So if you plug in tensor products, you get the sum of the individual Renyi relative entropies. I suppose I should say I've defined the Renyi relative entropy for only these values. We talked about the limit as alpha goes to 1. It does have a nice formula when alpha goes to 0 and alpha goes to infinity. When alpha goes to 0, it's something called min relative entropy. And it's just like you add up the Q values that are in the support of P. And when alpha goes to infinity, it's something called max relative entropy. And it ends up converging to like log of the largest ratio of P over Q. So that leads to another nice property of Renyi relative entropy. They're ordered. So as alpha increases, the value increases. And that's why these names min and max relative entropy came about.
Can I ask another question?
Yeah.
So for this data processing, does it have to be the same n on both, or can it be n yx of px and m yx of qx?
It has to be the same n. The interpretation there is that if you're doing an experiment and you don't know whether your system is in this classical state P or Q, there's a certain distinguishability. And to figure out, like in hypothesis testing, you're trying to figure out whether your system is in this classical state P or Q. You can do like a classical process to figure that out. So the interpretation here is that if as part of your classical process to figure out which one was prepared, you first do this channel, that's not going to help in distinguishability. It's an interesting question that you have. I don't know the answer to it, like what kind of statement you could make if you have different channels. Because like, I think if you allow general channels, you're not going to be able to make any kind of statement. Because like, you could just trace out this one and make it, like you could do the identity here, you can make this one trace out, oh, I'm sorry. Maybe I'll just punt on this one. I think I messed it up. But I think in general, if you allow that kind of thing, it's too much freedom and you won't have a data processing inequality. Okay, so let's talk about the quantum case. I think everyone knows this. Maybe I'll go fast. Quantum state, positive semi-definite unit trace operator. I'm going to use this subscript notation to indicate that the state rho is a state of a quantum system A. We call it density operator. We'll use D to denote the set of density operators. And the classical case is a special case in which the density operators are diagonal in a common basis. Okay, and quantum channels, again, this is standard stuff, I'm just stating it. Quantum channel is a complete positive trace preserving map. How do you check complete positivity? You act on one share of a maximally entangled state with the channel, and if the resulting choice state is positive semi-definite, then that is a test for complete positivity, necessary and sufficient test. And furthermore, it's trace preserving if on this choice state, when you trace out the output, you get the maximally mixed state. And then again, just to talk about the classical case, that's a special case in which the choice state is diagonal. Okay, quantum relative entropy. You know, what's kind of remarkable is, you know, von Neumann came up with quantum entropy before Shannon. I believe that was 1927, around that time. And then it took a long time before people thought about quantum relative entropy. A lot of people will call this formula the von Neumann relative entropy, but he didn't have anything to do with it other than his formula was a special case. Maybe that could be debated, I don't know. But the first formal paper about this was from Umegaki in 1962, where he proposed this formula. And it was a long time before the first proposal of this formula and the interpretation of it as like the correct quantum generalization of classical relative entropy. That was also Petz and his co-author Hiei in the strong converse from Ogawa and Nagaoka. Okay, so what are the special cases? The von Neumann relative entropy, similar to what we did in the classical case, we'll now plug into the second slot the identity operator and put a minus sign in front, and we get the von Neumann quantum entropy. Mutual information, that was from someone named Stratinovich in 1965. It's also, you know, kind of straightforward generalization of the classical formula. You plug in the joint state into the first slot and the product of the marginals in the second slot. And again, you can have this optimization over the marginal on B, okay? And then I guess sometime after, you know, Umegaki was 1962, then Lindblad proved that the quantum relative entropy does not increase under the action of a channel. And a core part of his proof was using the strong subadditivity inequality for quantum entropy. Okay, so there are at least two ways you can generalize the classical Renyi relative entropy such that the resulting formulas have operational meaning. They have some kind of physical interpretation, okay? There are other ways that you can generalize it, but those other ways are not known to have operational meaning. And that's still the topic of open research. Okay, so the Petz Renyi relative entropy, this is perhaps the most straightforward way you can generalize the classical formula. You replace the sum with the trace, you replace the p of x to the alpha with rho to the alpha, you replace the qx to the 1 minus alpha with sigma to the 1 minus alpha. And we're also going to allow for, you know, in the first slot, a state, the second slot, a positive semi-definite operator. Okay, so what are the properties of the Petz Renyi relative entropy? Similar to what we have in the classical case, but there are some differences. So the first is, you know, very important that as we take alpha to 1, we connect with the standard formula for quantum relative entropy, which has an operational meaning. So that's a first hint that this formula, d alpha, has the possibility of having an operational meaning, you know, that it connects to something that does have an operational meaning. The next is data processing. That is, another very important property. But here, the range for which it holds is restricted. Okay, it's restricted alpha between 0 and 2. And that's the first hint that this quantum generalization will not have any operational meaning for alpha greater than 2 if data processing does not hold for a larger range. Okay. Next is additivity. That's pretty straightforward. You just plug in and you kind of see that. The next is that they're ordered. I don't know how long this was known, but I became aware of it through Milan Masoni and Fumio Hiai's paper in 2011. Okay, and they're ordered for all alpha. Okay, the next generalization that has an operational meaning is what we call sandwich. This was done by 2 separate groups. I'm the W and WWY. It's a rare example of what we go alphabetical. I'm the first author, so that was kind of interesting. This was Wilde, Winter, and Dong Yang. Okay, so that's this formula. It looks more complicated, and when you first look at it, it's not obvious that this would have an operational meaning, but it turns out that it does, and it's been very useful for the past roughly decade, both in information theory and resource theories and physics. Okay, so you can define it for alpha between 0 and infinity like we did before. We call it sandwich because you take rho and you sandwich it with sigma with the relevant powers, and at the very least, it should be such that when you plug in commuting density operators, it reduces to the classical Renyi relative entropy formula. Okay, and then we put a tilde to distinguish it from the Petz formula. Okay, when we take alpha go into 1, again, we converge to the quantum relative entropy. So even though we have a very different formula, we still converge to the same quantity in the limit as alpha goes to 1. Okay, we also have data processing, and then the range is different from what we had for the Petz Renyi relative entropy. We have it all the way from 1 to infinity, but only from 1/2 to 1. So there were a number of papers that gave certain ranges, and then Rupert Frank and Elliot Lieb came in. And this was kind of remarkable. It was like 2 weeks after the papers came out that defined these quantities. These guys uploaded a paper that proved the data processing for the full range. I think they just had a tool, and it was ready to go. And as soon as they saw this, they realized, oh, we can just use that and apply it. So that was pretty interesting. Also, Salman Begi was very fast in the archive, proving the data processing with a totally different method for alpha 1 to infinity. Okay, it's also additive, and it's ordered. That was something important that Mueller, Leonard, Frederick Dupuy, Marco Thomas-Michel, that they figured out in their paper. Okay, so we've done a lot of definitions, and let's talk about some applications. And the first very basic one, the first thing that you can take from this talk is you can realize, oh, now I have a sense of how to prove what's called the quantum Stein's lemma, okay? And let's talk about what that is. So here, this is directly related to what I was talking about with Alexei a few minutes ago. So it's hypothesis testing. We imagine a quantum system is prepared in the state rho or sigma, and you don't know which one it's prepared in, but you know it's definitely prepared in one or the other, okay? And here, there's no prior probabilities. It's either definitely one or the other. It's just that you don't know it. So you're allowed to make a quantum measurement to figure out which state the system is prepared in. And then let's say, if you get the outcome lambda of this measurement, that corresponds to saying, okay, I'm going to guess rho. If you get the outcome identity minus lambda, that corresponds to guessing sigma. Okay, so then with this notation, in the statistics terminology, a type 1 error is when you say it's sigma when in fact it's rho. And then if you look to radar people, they'll say that's false alarm. Okay, and then the other kind of error is the probability that you guess rho when the state sigma was prepared, and the radar people will call that missed detection.
Mark, a question: what breaks the symmetry here between, like, why do you call one false alarm when the other one missed detection?
It doesn't really matter that much. I mean, like, oh, what breaks the symmetry? We're going to get to that on the next slide. Yeah, so that's a very good point. We're going to be talking about something called asymmetric hypothesis testing, and that's different from symmetric hypothesis testing. So I think on the next slide, you'll see the answer. Okay, so this breaks the symmetry. So we're going to say, we're going to talk about this kind of quantity where we demand that the type 1 error probability be no larger than epsilon. Okay, and then subject to that constraint, we minimize the type 2 error probability. So is that good for you, Alexi?
Maybe, let's see. So that's next requirement, right? You want to make sure that one of the errors is small, and subject to that, you minimize the other. Is that what you said?
That's right. Yeah. Okay. So this is what the kind of thing you're interested in a radar application, where, like, maybe there's something out there, and you don't want the alarm to be ringing so much. So you make a constraint for the type 1 error probability, but then, subject to that tolerance you're willing to allow, you try to make this other kind of error as small as possible. So that does break the symmetry. So epsilon can be any number between 0 and 1. Okay. So again, we're going to go with this convention where we allow sigma to be positive semi-definite. When we do that, we start losing the connection to physics, but then we end up with interesting information quantities that we can, generalize this formula with. But for the discussion of hypothesis testing, rho and sigma are quantum states. Okay, this quantity obeys data processing, and it's the same argument that I was telling Alexi earlier, where, if you're doing this measurement, one thing you can do before doing the measurement is a quantum channel. And then when you do so, your distinguishability will not be improved. And that's basically the proof of the data processing inequality. And you can work through the math, using channel adjoints and such kind of things with their properties to prove that. But that's the basic idea. Okay, so what is the quantum Stein's lemma? Here, what we're interested in is you plug in tensor powers of the states. So now it's like we're allowing repetitions, such that when you do so, it introduces more symmetry into the problem, and then it's possible to find these kinds of limits. Okay, so what we're doing here is we're interested in the optimal error exponent, right? So if I switch around this formula, or if I put 2 to the minus here, 2 to the minus dh epsilon, and then I just have this infimum, then you see that this quantity is an error exponent, okay? So then what we're interested in is, if you repeat, if you allow for tensor power states, how fast can you make that exponent decay with increasing n? Okay, so that's what this formula is saying, and it's just a compact way of writing it, such that when we start going through the math, you just take limits and infimums, and then you just see that it falls out. But you should think of it as the optimal rate at which the type 2 error probability can decay with increasing n. So that's an interesting and meaningful figure of merit. The other kind of quantity is the strong converse rate. So that's what you get when you just flip the imps to sups, okay? The other thing about this quantity is that it's well defined mathematically. You know, like if we have a sequence if we have a sequence, then the limit is not necessarily always well defined, but these things like lim-inf and lim-sup are always well defined, and as well as infimum and supremum. Okay, so from the definitions, you see pretty quickly that this optimal achievable rate is always less than the optimal strong converse rate. And what the quantum Stein's lemma says is that they both collapse to the same value and they're equal to the quantum relative entropy. So that is the fundamental operational meaning of the quantum relative entropy. So you should just think that, oh, it has a meaning in asymptotic hypothesis testing. So if we're willing to allow for tensor powers of states. And also, one thing you should realize is that in this formula, in this task, we're allowing for collective quantum measurements. So we're allowing for measurements that act on many quantum systems, even though that might be extremely difficult to do experimentally, right? Like you would need a quantum computer to do those kinds of measurements in general. Okay, so
sorry,
yeah.
I have one question. Are the epsilons at which the infimum and supremum achieved the same?
That's a very good question. We're going to see that in the next few slides.
Okay.
The formula is true regardless of the value of epsilon. So any value of epsilon in the open interval from 0 to 1. If you set epsilon to 0 or epsilon to 1, it kind of like trivializes the problem. But as long as you have an epsilon that's bounded away from 0 or 1, then they all collapse to the same value. So that's a good question. That's something that we'll see. Yeah. Okay. So I'm not going to prove everything because that would take too much time. But one thing that's very interesting is that there's a direct relationship for a single shot rho or sigma without tensor powers between the hypothesis testing relative entropy and the Petz Renyi relative entropy. And that can be distilled from the first, it was really there in the second paper and it was like rediscovered in this other paper. So that's very interesting. And that's the key thing that'll connect us from hypothesis testing to Renyi relative entropy. And then you kind of see what we were just talking about, that this lower bound becomes trivial if epsilon is 0, right? On the other end, we have an upper bound that relates hypothesis testing, the operational quantity, to the sandwich Renyi relative entropy. And there's a certain beauty that I find with these formulas, because you just do some flips of Petz to sandwich and epsilon to 1 minus epsilon you get from the lower bound to the upper bound. But they do have very different proofs. This one is much simpler. You just use data processing and you pretty much get it. This one, you need some powerhouse matrix inequality that was derived by Konrad Audenart. Okay, so let's apply the lower bound, and how we're going to do it, we're just going to take the definitions and just work a bit with the math, and then we'll arrive at the conclusions. So let's plug in the tensor power states. Let's use the lower bound. We're going to divide by n in front because that's how the operational quantity is defined. Okay, when we do that, we use the additivity, and then this term collapses to the Petz Renyi relative entropy. And then at that point, you're pretty much done. You take the n infinity limit, this term goes away. The lower bound holds for all alpha between 0 and 1. You take the supremum, since it holds for all alpha between 0 and 1, you can take the supremum over all such values, use the ordering property, and the fact that the limit as alpha goes to 1 converges to the relative entropy. So that's the first part of the Stein's lemma, pretty fast. Okay, and that's, you know, this fundamental theorem in quantum information theory. For the other part, use the upper bounds, right? So use the upper bounds, use the additivity of the sandwich Renyi relative entropy, take the limit as n goes to infinity. The upper bound holds for all values of alpha between 1 and infinity. Since it holds, this is a typo, I meant to say upper bound. Since it holds for all alpha between 0 and 1, take the infimum over all those, use the ordering property, and the limit as alpha goes to 1. And boom, you have the upper bound, you have the relative entropy as the upper bound. And then related to the previous question, you see that we can do these tricks for all alpha strictly between 0 and 1, right? And so that's what we get here, that there's something slightly stronger. We don't, this holds for all alpha, for all epsilon between 0 and 1. So that's the quantum Stein's lemma. Okay. And then that's the core interpretation of quantum relative entropy. This result was figured out by Hiai and Petz in 1991. They had a different kind of proof. The strong converse was figured out by Ogawa and Nagaoka in 2000. And then that was the big hint in 1991 that this formula for the quantum relative entropy would be the right formula from which you could construct all other kinds of quantum entropies that now have meaning in quantum information theory. Okay, so that might be a natural stopping point if there are questions. How are we doing on time, Carl? I can't, I should have my cell phone here, but I didn't put it there.
So we are 40 minutes in.
40 minutes in, okay, good. So we'll probably have time just to talk about the entanglement-assisted capacity application, and then maybe I'll just like very, very fast breeze through the final one. Are there any questions? Okay, let's move along. So I want to generalize what we were talking about previously. This is something we do a lot. Let's just say that any function that obeys data processing, let's call that a generalized divergence, okay? And then from that, we can get kind of general constructions of information measures and entanglement measures for entanglement theory. Okay, so examples of functions that obey data processing. We already talked about relative entropy. We talked about Petz and Sandwich Renyi. And we talked about even the operational quantity hypothesis testing relative entropy. But other things like trace distance, and if you flip the direction of fidelity, you get, you know, they obey data processing. Okay, so then we can make generalized mutual information of a bipartite state with the same kind of construction like we did previously. An alternative one is like this. I'll put a bar above it, and that just indicates there's no optimization over the B system. Okay. And then you can also construct entanglement measures, right? And so this idea was already kind of there in the early work on relative entropy of entanglement of Vidral and Planio. So what we'll do is just take the generalized divergence and minimize over separable states. Then we get generalized divergence of entanglement, which just generalizes relative entropy of entanglement. There's another kind of quantity which is interesting as an entanglement measure. You take an idea of Eric Rains from 20 years ago, and we can make generalized Rains divergence. So what you do is you increase the set of separable states to what we call these PBT prime operators. And these are operators that are positive semi-definite and such that when you take their partial transpose and the one norm, it's less than 1. And this is also a very interesting construction which leads to an entanglement measure. And it leads to the tightest upper bounds on the distillable entanglement of a quantum state. Okay. So that was just something I wanted to mention. That's actually relevant for the final part of the talk. But anyway, it's interesting. The other thing we can do is from these measures of information and entanglement for quantum states, we can generalize them to quantum channels. So what we do is we take the state measure, so we take mutual information, and if you optimize it with respect to all states that are going into a channel, right? So Alice could prepare a bipartite state, send one system to the channel, and then you get some bipartite state, you plug it into the mutual information, you optimize that. That's what we call generalized mutual information of a quantum channel. Okay. And then, in fact, you can take any of the state measures that we talked about earlier in the same kind of construction and make channel measures that way, okay? And so it could measure different properties of the channel. It could measure how much entanglement you can generate with the channel, how much classical information you can create with the channel. And you know, so this kind of construction is useful. Okay, let's talk about the next application. And this is where I just want to show the use of these Renyi relative entropy formulas and how you get on the surface simple proofs for these nice results. And I picked out entanglement-assisted capacity because that's a task for which we have the nicest answer in quantum information theory. It's an answer that works for all quantum channels. Okay, so what is the task? Alice and Bob are connected by a quantum channel. And then, sorry, this starts looking like a lot of math. Maybe I'll jump to the picture. Okay, so this is the picture of entanglement-assisted communication. Alice has a classical message that she wants to transmit to Bob using a quantum channel. They share entanglement beforehand. Okay, this is separating Alice's lab from Bob's lab. Alice acts with an encoding channel on her classical message and her share of the entanglement. That gets input, that outputs a system that can be input to the channel, right? So the channel could be like a bosonic loss channel that models free space propagation or communication through a fiber optic cable. Then Bob is on the receiving end, he gets some output. What he does is he combines his output with his share of the entanglement, does some collective measurement to estimate the message Alice sent. So in math, this is what that looks like. So we defined, you know, a code to be the number of messages that you want to send and the error that you tolerate, okay? And it consists of the encoding, that's what I drew on the previous slide. This is the maximally classically correlated state. You can think that the task is just to establish classical correlations between Alice and Bob, you know, and then what you want is that the final classically correlated state at the end of the protocol to be indistinguishable up to an epsilon error from the ideal maximally classically correlated state. Okay, that's the task of entanglement-assisted classical communication. And then how do we define capacity? So we can define the one-shot capacity like this. You fix epsilon, you fix the error, and then you ask, what is the largest number of bits that you can send over the channel such that there exists a code of the form that I talked about on the previous slide. And then we can define capacities like we did for hypothesis testing, right? So plug in to this formula, the tensor power channel. Now we're allowing for many repetitions, many uses of the channel, and then we divide by n to get a rate of communication. So this capacity is measured in bits per channel use. And then we're allowing for a large number of channel uses, and we want in the limit, you know, that the error tends to 0. So this is a very compact way that you can define capacity that's equivalent to other standard definitions of capacity. And we also have the strong converse, which is of interest for reasons that we were talking about in hypothesis testing. Like, you know, it could be the case that the formula would be the same regardless of the value of epsilon, right? And so that kind of thing happens again for the entanglement-assisted capacity. So what it shows is that, well, what we'll conclude eventually is that the capacity is a very sharp dividing line between rates of communication that are possible and rates that are impossible. Okay, and then from the definitions, we always have that the capacity is less than the strong converse capacity. So in the next two slides, I'm going to have an analysis that's pretty similar to what we had for hypothesis testing. And it's really just to give you a taste of it. There are techniques that are used, and that's what's embedded in these references here. There's a technique called position-based coding. It's actually a very interesting quantum generalization of a classical technique called pulse position modulation. And I would need, like 20 minutes to talk about that properly. So I won't do that here. But an interesting backstory is Nakib Warsi, one of the co-authors of this. He told me that he was studying my textbook and he thought that the proof was too complicated. And then he came up with this other method, and it's much simpler and it's very beautiful. And what's really nice about it is that it gives you nice formulas even in the one-shot case, when you're just trying to send classical information over a single use of the channel. Okay, so that's how this formula came about. You use this position-based coding method and something else called sequential decoding, that's where if you're Bob, you do a first measurement to ask, was the first message sent? And then you get yes or no. Then if you get no, then you do a measurement to ask, well, was the second message sent? And then you keep repeating this over and over again. And so that's a technique that can be used. It's very analogous to what's used in classical information theory. But what's different and interesting about the quantum case is that even though you do a bunch of measurements, it's possible to show that if you do the right kind of measurement, you're not going to damage the state too much from one measurement to the next. Okay, so there's a lot of stuff going on in this formula, and I just kind of described it quickly. Okay, but this right here is that mutual information formula, mutual information of a channel that I talked about previously. We put the bar to indicate that you don't optimize over the second slot in the relative entropy. Okay, and then Will Matthews and Stephanie Vayner had a very nice paper where they proved the one-shot converse. So they proved that the one-shot entanglement-assisted capacity is bounded from above by the hypothesis testing mutual information of the channel. So that's very interesting. And the way that they did it is very roughly is they related the communication task to hypothesis testing. That kind of idea has been known for a long time, since 1975. I think Robert Gray was a classical information theorist, had a paper about relating communication to hypothesis testing. And so a similar kind of concept is being explored here. And so what's nice is you get formulas that are relevant for the one-shot case. Okay, so then once you have those, you can just use properties of the Renyi relative entropies in a very similar way to what we did for hypothesis testing. What I can do is, in this formula in the previous slide, we have this extra parameter eta that we can optimize over. To get the asymptotics, I'm just going to plug in eta equals epsilon over 2. When you do that, you get this lower bound, and then I'm plugging in the tensor power channel, okay? And then this kind of lower bound is we get just from using the lower bound of Renyi relative entropy, Petz Renyi relative entropy on hypothesis testing relative entropy. It's a very similar argument, okay? So, and then here you use superadditivity of the Petz Renyi relative entropy of a channel, okay? What becomes more challenging when you're dealing with these formulas for the case of quantum channels is relating the tensor power channel to like getting the additivity kind of result, okay? But for this case, it's pretty simple to go from one step to the other using the stuff that we talked about previously, okay? Then again, you use the definition of capacity, take the limit. All this stuff washes away as n goes to infinity. And And then you're left with this very nice lower bound that holds for all alpha between 0 and 1. And then you can do the same kind of thing. Take the limit as alpha goes to 1. And then you get the mutual information of the channel as a lower bound on the rate at which it can communicate. And that was regardless of the value of epsilon. Okay. So then we can conclude from this in definitions that the mutual information of the channel is a lower bound on entanglement-assisted capacity. For the upper bound, similar kind of reasoning. We use the one-shot upper bound from Will Matthews and Stephanie Vayner. We then use the relation between hypothesis testing relative entropy and sandwich Renyi relative entropy to get this. Here, this is not trivial, this equality. Here you need additivity of the mutual information of the channel, okay? There's a lot of interesting math. There was essentially a whole paper that was behind that. And we used results of Marius Junge et al. From 2006. Okay, but then once you have that, you take limits. You take the limit as n goes to infinity. You get that this upper bound holds for all alpha between 1 and infinity. And then similar kind of thing. You get the mutual information of the channel. Okay, so what we conclude from that, the entanglement-assisted capacity for all quantum channels, very beautiful formula in terms of the mutual information of a channel, and you get the strong converse holds also. Okay, so regardless of the value of the error that you're willing to tolerate in communication, asymptotically, the optimal rate of communication converges to the mutual information. Okay, I should state, that the first equality, that the capacity is equal to the mutual information, this was found by Bennett et al. In a famous paper from 2002. And then, others, this was Bennett et al., this was Maria Berta et al. They had techniques that established the strong converse. But these other proofs with Renyi relative entropies, that kind of stuff came later. Okay. How are we on time, Carl? Oh, is there a question? Something in the chat.
Yeah, we had a question from Eddie. He asked, how does this change when we do not consider the asymptotic capacities?
So by this, maybe Eddie can clarify the question a bit.
Right. Yeah, I mean, so we take the n to infinity for these proofs, right? But like,
yes.
What if it's finite? Or
right. So that's a very good question. If n is finite, you can plug in tensor n to these formulas and divide by n, right? And then you'll get rate. And if n is small, like 1, 2, 3, 4, 5, maybe up to 10, I don't know. The value of this quantity can be solved by a semi-definite program. And the same for this upper bound. That can be solved by a semi-definite program. So for a small number of uses, you can figure out these limits, this lower bound and this upper bound using an ordinary computer. But then as n starts getting larger, it gets harder. So then, when n starts getting larger, there's a whole area of information theory, of quantum information theory that has emerged called second order asymptotics. That started in 2012 with work of Marco Tom-Michel and Masahito Hayashi and Kei Lee. And, in this capacity formula, right here, this is identifying the first order term in like an asymptotic expansion of capacity, okay? Mm-hmm. So there's a second order term that will have a leading order term of 1 over root n, and that gives you a sense of what you can achieve for finite n as well. And that would be a whole other discussion and talk, but I can point you to papers about that. I had a paper called on the second order asymptotics of entanglement-assisted communication. The reason we did that is because we felt like we had not solved the problem in full. And there are still open questions there about identifying the second order asymptotics of entanglement-assisted capacity. That's a very nice question that should probably have a solution at some point. It's just we don't know how to do it.
Okay, thanks.
Okay.
Okay, yeah, and as far as time, so we're pretty close to the end. So Eastern time, it's 11:58.
11:58. Okay. So I'll just wrap up. What I want to mention is a third formula that is very interesting, and it's now being called geometric Renyi relative entropy. This was a formula proposed by none other than Petz and Renyi in 1998, and Keiji Matsumoto played an important role. What does the formula look like? It looks like this. So it's another generalization of Renyi relative entropy. For years, it was not clear that this was useful for anything. Why is that? If you take the limit as alpha goes to 1, it converges to something called Bolovkin-Stashevsky relative entropy. This was invented by those authors in 1982. And for years, I jokingly referred to this as the BS one, because it wasn't clear if it meant anything or was useful for anything. But its use has now been found in a very strong way. A paper of Kun-Fang and Hamza Fawzi, they have shown that it's useful for feedback-assisted capacities, for providing very good upper bounds on feedback-assisted capacities. So that's the main thing I wanted to say about that one. And there's a whole section of the talk dedicated to that. It's called geometric Renyi relative entropy because you can rewrite it in terms of something called operator geometric mean. Okay, so I'm going to skip through all this stuff. And maybe I'll just show you a picture. If you're interested in the capacity of a channel assisted by local operations in classical communication, that's very relevant for distributed quantum computation and, let's say, quantum networks. The geometric Renyi relative entropy is useful in giving an upper bound on this kind of assisted capacity. Okay. And yeah, this is the main statement I was making there. The main, the assisted capacity is upper bounded by something called geometric Rain's divergence of the channel. And then this can be efficiently computed with semi-definite program, etc. Okay, so what I talked about were 3 quantum generalizations of Renyi relative entropy and their use. The first was the Petz Renyi relative entropy. We showed how it's a lower bound for distinguishability in communication tasks. The other one we talked about was the sandwich Renyi relative entropy. That was useful as an upper bound for distinguishability in communication tasks. And then the final one I breezed over quickly is the geometric Renyi relative entropy. And then I just kind of stated quickly how that's useful for feedback-assisted tasks. Fang and Fawzi showed that this is useful for bounding. You can think about a quantum Stein's lemma for quantum channels, right? So it's like, you're allowed to interrogate a channel and you're told it's going to be one channel or another, and you're trying to figure out which one it is. And you're allowed to do adaptive operations between every call to the channel. So this is the kind of thing that could be useful for what is sometimes called quantum radar applications, okay? And this geometric Renyi relative entropy is useful as an upper bound for distinguishability in asymptotic quantum channel discrimination. Okay, and then for future directions, I guess a clear question is, are there other interesting quantum generalizations of Renyi relative entropy? Do they have applications? There's a whole family that are called alpha Z Renyi relative entropies. This was presented by Konrad Audnart and Nilanjana Datta. And the full range of data processing for these parameters for which it holds, that was only solved recently by Haonan Zhang. And maybe that gives me an opportunity to plug something. In early November, actually Friday, submissions are due to the Beyond IID conference. And you know, if you found this talk interesting, you can get much more of this kind of stuff at the Beyond ID conference. The submission deadline is by Friday, and then the conference will take place in early November. Okay, and I'll stop there. Thank you.
Great, thank you. So I'm going to go ahead and stop the recording.